Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of palindrome partitioning min-cuts. This question basically gives us a non-empty string and asks us to find the minimum number of cuts that we need to perform on this string such that every remaining substring is going to be a palindrome, meaning that it's going to be written the same forward as backward. Okay, so in front of me here, I've got an example, noon ABBAD, and the answer for this string is going to be 2. We can put a cut right after noon, we can put a cut right after ABBA, and the 3 resulting substrings are going to be palindromes. Noon is written the same forward as backward, ABBA the same, and D is just a single letter, and a single letter is considered a palindrome because it's written the same forward as backward. Now, this question is pretty difficult, mainly because compared to other questions that deal with numbers, like maximum increasing subsequence in an array or the longest increasing subsequence, and numbers, we tend to be kind of familiar with numbers, right? Here, we're dealing with palindromes, and we're dealing with this idea of the minimum number of cuts, and that can be pretty tricky. To give you an example here, even though we can cut the string into 3 substrings, right? Noon, ABBA, and D, we only need 2 cuts. We need 1 cut less than the number of substrings remaining, and that can be kind of tricky to wrap your head around, especially in the setting of an interview. But also, the reason that this question is difficult is because it's got a naive solution that's already difficult in and of itself, but that's kind of the solution that most people will end up finding. And then it's got a more optimal solution that is a lot more difficult to implement and a lot trickier to come up with. But let's dive into it. Let's see if we can plow through it, and let's try to understand how it works and how it can be solved using dynamic programming. So how did we get to this answer, right? That noon ABBAD has 2 cuts. That's the minimum number of cuts that we need. Well, the first thing we want to do, and you probably guessed it here when you saw the name of this question, is we want to find the palindromicity, in other words, whether or not a string is a palindrome, of every substring in our input string. Okay, and to do so, we're going to use a 2D array, which I've kind of constructed here. And in this 2D array, we're going to store the palindromicity of every substring in our input string. Okay, so the way we're going to do that is that at any given index, let's say this point here, the row will represent the starting index of our substring, and the column will represent the ending index. So at this very first point in the array, 0, 0, we're going to get the string that starts, or the substring that starts at index 0, so starts at n, and ends at index 0, ends at n. Okay? And so we're going to store the palindromicity of n at this point. Then at the next point, we're going to store the palindromicity of the string that starts at index 0 and ends at index 1. So that's going to be NO, right? And all the way through the array, you can store every substring. Here, at this point here, we're going to pretty much store the palindromicity of our entire string. The string that starts at index 0 with N and ends at index 8 with D. So, how do we do that? Okay? Well, a simple way that might be fairly straightforward to you, might have even popped out, is to kind of iterate through our array, do kind of double for loops, get every substring in our array, and for each of those substrings, call some kind of isPalindrome function, right? A helper function that's going to check whether or not that substring is a palindrome. And that would be a pretty fair approach to this problem. In fact, that's the one that we're going to implement for the time being. So what we can do, and here I guess I'm going to write kind of pseudocode, we're going to say for our index I, right, which is going to be between 0, it's going to be less than or equal to 0, and it's going to be less than the length of our string. So for every index in this range, for every index I in this range, and then for every index j, that's going to be, so j is going to be between I and the length of the string. So I is going to be our starting index. So I is going to represent the rows in this array. And j is going to be our ending index. It's going to represent the columns in this array, in this 2D array. So for in both of those for loops, we're going to say palindromes. Let's call, by the way, our 2D array that we're building palindromes. So let me just put an arrow here. This is going to be palindromes. So palindromes at index I, j is going to be equal to, and here we can call our isPalindrome function, which is a helper function, isPalindrome. What is palindrome? Well, the substring that starts at index I and ends at index j. So here we can do something like string, and now I guess I'll write it in Python. We slice it from I to j plus 1 because j plus 1 is exclusive, right? So you want to go from I to j. And that's that, right? With this little double for loop shenanigan that we've got here and our isPalindrome function, we can pretty much build up this entire 2D array. And so right now we're going to do just that. Let me move this formula here that we've kind of understood. It's pretty straightforward. Move it to the top, and we're going to build up this array. I'll denote true, so whether or not a substring is indeed a palindrome with a T, and then I'll denote false with an F. So let's kind of build this up pretty quickly. We start at 0, 0. That's the substring that just starts at n, ends at n. Is n a palindrome? Yes, it is, because it's a single letter, so we can put true. Then, is no a palindrome? No, it's not. Is NOO a palindrome? No, it's not. Is noon a palindrome? Yes, it is, right? Noon, as we stated in the solution here, noon is written the same forward as backwards, so this is going to be true. Noon A is not a palindrome. Noon AB is not a palindrome. And then I believe none of these are going to be palindromes. Then we move on now to the second row. So here we're starting at index 1, right? So, and then our index j is going to start also at index 1 because the j is greater than or equal to I. So O is indeed a palindrome. So here we can put true. OO is also a palindrome. OON is not a palindrome. OONA is not a palindrome. And here I believe the rest, the rest is probably going to be false here. Okay. Now we move on to the third index, right? We start at the second O. So O is a palindrome. ON is not a palindrome. ONA is not a palindrome, and I think the rest are all false. Hope I'm not making a mistake here, but I think this seems fairly intuitive, right? Then we move on to this index 3 here, where we have another n. So this is going to be true. By the way, you can notice here that the entire diagonal here is going to be all trues, right? Because a single letter is always a palindrome, so we can fill those out to be all trues. But so true, then NA is false, NAB is false, 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 false. Then we have A is indeed a palindrome, AB is not a palindrome. ABB is not a palindrome. ABBA is a palindrome, so this is going to be true. ABBAD is not a palindrome, so that's going to be false. Then we have B, that is a palindrome. BB is a palindrome. BBA is not a palindrome. BBAD is not a palindrome. Now we're at the second B, right? We're here. So B is a palindrome. BA is not a palindrome. BAD is not a palindrome. Then we're at the A. A is a palindrome. AD is not a palindrome. And lastly, D. D is a palindrome. So we've built our 2D array. I mean, it's kind of the 2D array. I guess there's an entire half that we're not really using, but it is a 2D array at the end of the day. Kind of acts as a 2D array. It's the same amount of memory and the same amount of time complexity to build up. And we've got it. This tells us at every index what is a palindrome, right? So now what do we do with this? What do we do with all these substrings whose palindromicity we know? Well, now we want to find the minimum number of cuts, right? And to do so, we're also going to use dynamic programming. Because here I guess we didn't really use dynamic programming here. We just built up this 2D array, but we didn't use any previous solutions to find next solutions, right? So we haven't really applied real dynamic programming techniques thus far for this portion and for this sort of solution. This, by the way, this is the kind of straightforward solution that we mentioned at the beginning. So let's build up now a new array that's going to hold the minimum number of cuts. So let me erase this and let me move this big array here. Let me make it smaller. And let's move it here. Whoa. Let's grab it. Okay. Let's move it here. So we're now going to build up an array that's going to have the same length as our input string, as noon ABBAD. And it's not going to be two-dimensional, right? It's going to be just one-dimensional. And it's going to hold at each index the minimum number of cuts needed for the substring that starts at index 0 and that goes all the way to the index that we're at. In other words, if I build out this array here, let's build it out here. And remember, we had 1, 2, 3, 4, 5, 6, 7, 8, 9 letters in our string. So at each of these 9 indices in this array, we're going to store the minimum number of cuts needed for the substring that starts at index 0. So it always starts at n and goes all the way to that index. So in the first index here, we're going to say the minimum number of cuts needed for the string n. Then in the second index, the minimum number of cuts needed for the string no. Then NOO, then noon, then noon A, noon AB, etc. All the way to our final string. So to initialize this array, we're just going to put infinity in it. So we're going to put infinity 9 times. 4, 5, 6, 7, 8, 9. Why are we putting infinity? Well, we're saying, hey, at the very beginning, we don't know how many cuts we need for each substring, right? To turn it into just remaining strings that are palindromes. So let's just assume that we need an infinite amount of cuts. And this is just going to help us out for when we kind of apply a formula. Or actually, this might not even help us out. This is just going to kind of, this is kind of our filler, our filler array at the beginning. Okay, and so now, how do we actually find the real values that need to be in this? Okay, well, we start at the first one, and we say, is the substring that we're looking at here an actual palindrome, right? So for this index 0 at 0 here, we're looking at the substring that starts at index 0, ends at index 0. So it's just the letter n. Here I'm underlining the letter n at the top. Is this substring a palindrome? It turns out in our case it is, right? N alone is a palindrome. So if it is a palindrome, then we know how many cuts we need, right? We just need 0 cuts. If a string is already palindrome, then we don't need any cuts to get all the remaining substrings to be palindromes. So whenever we get to a string that's a substring that's a palindrome, we just store 0. So here I'm going to erase this infinity, and I'm just going to store 0 because n is a palindrome. Okay? So now we get to the second string here at index 1. So now we're looking at NO. Okay, is NO a palindrome? No, it's not. By the way, when I'm asking, is it a palindrome, we're not just making this up, right? We're not pulling this out of thin air. We're looking at our array here, and we're saying, is NO a palindrome? Let's look at our array. It was here. NO was in the second index. It was false. So no, it's not a palindrome. So if it's not a palindrome, well, what does that mean? If our current string is not a palindrome, and we know what the minimum number of cuts was for the previous string, right, for the string without this letter, which was n, well, we could say, okay, then the cuts is going to be however the minimum number of cuts was for that previous string, in this case n, plus 1, right, because we could put 1 cut here in between and get n and no, right? So it's going to be, in this case, it's just going to be 1, right? We're going to take whatever the minimum number of cuts was before, which was 0, plus 1. Okay, seems pretty straightforward, but wait, that's not actually our formula. Our formula is not going to be to actually only look at the previous string and add 1. Because let's look at the second example, right? Or this third example. Now we move to index 2. So we're looking at the string new, N-O-O. N-O-O is not a palindrome, right? If we look at our palindrome array here, we see that it's false. It's not a palindrome. So we could say, okay, look at what the minimum number of cuts was for the previous string, N-O, and add 1 cut in between here. And so that would be 1 plus 1, 2, right? So we can tentatively store here, instead of infinity, I'll put in green, we could tentatively store 2. Okay? But is that the answer here? And it turns out, no, it's not, right? Because, let me undo the things that I drew here. Is 2 the answer? Whoops, let me re-erase this and let me re-put 2. Is 2 the answer? No, it's not, because we could put 1 cut here between N and OO, and we would have 2 palindromes, because N is a palindrome and OO is a palindrome. So the actual answer is 1 cut, not 2 cuts. So how do we get to this 1 cut? How do we replace the 2 that we tentatively stored and replace it with 1 cut? Well, we say, okay, let's iterate now. Let's iterate through substrings that are going to start at, instead of starting at 0, like every substring here that's being represented starts at 0 and ends at whatever index we're at. But now we're going to say, let's iterate and check the palindromicity of every substring that starts at each subsequent index, and let's see if we can create a palindrome by adding the current letter that we're at. Okay, so that probably sounded really complicated, but what I mean is, let's take our example here. We're at N-O-O, and we know that N-O-O is not a palindrome. But let's say, wait, can we form a palindrome somewhere in between this, right? Somewhere in between this, can we form a palindrome by adding O to the end? And it turns out we can, right? Because, like, we know that N-O-O is not a palindrome, but now we start iterating through this array, and we look at through the string, and we look at what about the string OO, right? OO is a palindrome. So if OO is a palindrome, then let's look at the minimum number of cuts we needed for the index before our new started index, which is where the O is at. So let's look at the minimum number of cuts for this N, and see if the minimum number of cuts for this N plus 1 is going to be less than the current number of cuts that we've stored. And if it is, then we update it. So let's see this in action. Here we say, okay, let's iterate. Let's start looking at the string OO. OO is a palindrome. What was the minimum number of cuts at n, the index right before a new started index, which is O? Well, it was 0, right? So we do 0 plus 1, because now we're saying we're going to put a cut right, whoops, let me draw. We're going to put a cut right here, because we know that the string that comes after this cut is a palindrome. So we take the minimum number of cuts here plus 1 cut. So we get 1, and 1 is less than the 2 that we had previously stored. So we can erase this 2 and update it to 1. Okay? And that is our formula, that is our algorithm. So let's try to build up the rest of this array using this. So now we move on to, we're at noon, right? So is noon a palindrome? Well, we look in our array. Oh yeah, it turns out noon is a palindrome. It's true. So if noon is a palindrome, then okay, we actually don't have anything to do here. We can just store a 0. Okay, so simple enough. Now we move to the next point. Noon A. Noon A is not a palindrome. So what could we do here? Well, we could say either tentatively store, let's erase this, tentatively store whatever the minimum number of cuts was for the previous string, for noon, which is 0, plus 1, which would be putting a cut between the previous substring noon and our current letter A. So 0 plus 1 is 1. Let me put it in green. So we can tentatively store green. Or let's check if we can do better. How do we check if we can do better? Well, it turns out here, because this is going to be 1, we can't really do better. But let's just check for the sake of argument. What do we have to do? Well, we say, okay, let's start a substring at this index instead of index 0. Let's start at index 1. Is Una a palindrome? Is Una a palindrome? Well, let's look at a string that starts at index 1. So we're going to be on the first row and ends at index 2, 3, 4. So here. Is this substring a palindrome? No, in our array, we're told that it's not. It's false. So, okay, we just move on to the next one. Ona. Is Ona a palindrome? No, it's not a palindrome. Okay, so we move on to the next one. Na. Na is not a palindrome, okay? So we move on to here, and now we're back at where we were at with noon, a cut, and then A. Okay, so basically at every point here, we're trying to check, can we form a palindrome with the previous substring and take the minimum cuts from the string that comes before it and see if we have a better solution, right? And so now you can kind of see why this is a dynamic programming problem, because we really are using this array, we're using previous solutions to build up the next solutions, and we're using our palindromes array to help us along the way. So let me erase this value and let me put it in purple because it's final, 1. So now we move on to the next point. B. Is noon AB a palindrome? No, it's not. So we could tentatively put the minimum number of cuts. We could tentatively say, oh, we can cut here, right? We can put a cut here. What was the previous minimum number of cuts? Well, it was 1. So we would do 1 plus 1. That would be 2. And then we check all the other substrings. Can we form a palindrome from the other substrings? Is unab a palindrome? Well, we can look in our array. No, it's going to be false. Is onab a palindrome? No. Is nob a palindrome? No, etc. And so you can see that now this 2 is final. So fairly straightforward. Now we get to the next point. We're at noon ABB. And this is going to be a kind of telling example, because here we could say, hey, we could put a cut here, right? And in that case, we look at the minimum number of cuts from the previous string, which is 2, plus 1 cut. So we can put tentatively 3, but it's going to turn out that this 3 is not going to be the actual answer here. We could actually have only 2 cuts, right? Because if we start iterating through other strings, and we see that un ABB is not a palindrome, on ABB is not a palindrome, NAB is not a palindrome, ABB is not a palindrome, but BB is a palindrome. So if BB is a palindrome, let's look at what would happen if we were to put a cut here before BB. We'd know that the minimum number of cuts for BB that is a palindrome is 0, right? So we would just need the minimum number of cuts for NUNA plus 1 from the cut that we put between NUNA and BB. What was the minimum number of cuts for NUNA? Well, it was 2. For NUNA, it was 1. It was right here, 1. So 1 plus 1 plus 1 equals 2, and 2 is less than 3. So we can erase this 3 that we had put tentatively, and we can replace it with 2. Okay? And now we get to the next point, nun ABA, right? Nun ABBA. So let me just try to erase this thing here. Whoops, I have to rewrite AB. So nun ABA, we could tentatively store this number where we have a cut right before the A, and we took the minimum number of cuts for nun ABB. Nun ABB was 2, right? We just computed it. 2 plus 1. So this is tentatively going to be 3. But here we can see that we can go back and start iterating. So UNABBA is not a palindrome, ONABA is not a palindrome, NABA is not a palindrome, but wait, ABBA is a palindrome, right? ABBA, we can even verify in our array. We start at index 4, we end at index 7, so we start at index 4, end at index 7. Yes, we have true. ABBA is indeed a palindrome according to our palindrome array. So what was the minimum number of cuts for the string right before ABBA for the string noon, right? We go down to noon. Oh, it was 0 because noon was a palindrome itself. So 0 plus 0 for ABBA because that's a palindrome plus 1 for the cut between noon and ABBA, and that's 1, right? And so we can, we know that the 3 that we had put here, we can replace it with a 1. And lastly, we get to our final point, D, where we're going to say, let's tentatively put a cut before the D. So we can erase this infinity, say, okay, we have 1 here. 1 plus 1 is going to be 2. We can tentatively store 2, or because we're saying tentatively, let's put it in green. Then we go through all our iterations, and we'll end up realizing that 2 is indeed the final answer. We'll never get to a point where we get something better than 2. So we can store 2 in purple as our final answer. And that's it. That is our main algorithm. Okay? Now, what's the time complexity of this algorithm? What's the space complexity? Well, the time complexity is not as straightforward as you might think, because we're doing a lot of things. First, or rather second, with this cuts array here, this array that holds the minimum number of cuts, we are doing an O then squared operation, right? Because the array itself has length n, where n is the length of our input string. But then remember, at each of these indices, if we're not dealing with the palindrome, we're reiterating through all the other substrings that come before it. So that's an O of n squared operation where n is the length of our string, or of our input string. So you could say, okay, it's O of n squared, but no, it's not O of n squared, because let's look at our palindromes array here that we built at the beginning. How long did it take to build this array? Well, you might be inclined to say, oh, that was also O of n squared, right? We had a 2D array that had the same number of columns and rows as our string has characters. So O of n squared, simple enough. But no, recall our formula, which is in the top right corner here. We're doing these double for loops, so we're definitely doing O of n squared computations. But what is each computation? Each computation is calling our isPalindrome function. And it's slicing a string, right? We're saying the isPalindrome string from I sliced to j plus 1. And it turns out that slicing a string is an O of n operation, and isPalindrome is also an O of n operation, right? Because you could argue, well, wait, maybe we don't have to slice the string, right? We could just give, like, the indices, 2 pointers, I and j, or j plus 1, to our isPalindrome function. But isPalindrome, no matter how you spin it, is an O of n time function, right? It's just, there's no way to go around that. So, or at least when you implement an isPalindrome function, there's no way to make it faster than that. So we're doing O of n squared computations, and then at each computation, we're doing an O of n operation that is palindrome. So that becomes O of n cube, right? O of n cube time, which kind of swallows the O of n squared that we had from the cuts array, right? And so our time complexity becomes O of n cubed. So time equals O of n cubed, where n is the length of our input string. What's the space complexity? Well, the space complexity is going to be O of n squared. Why is that? Well, we're storing 2 arrays. The second one just has length n, right? Because it's the same length as our input string. But the first one, the palindromes array, it's a 2-dimensional array, right? So it's going to be O of n squared. So our space complexity is O of n squared. Now, can we do better than this? And recall that at the beginning, I mentioned that this was a very difficult question because it had kind of a naive solution, which we just did, which doesn't seem that naive, by the way, because this solution in and of itself is pretty difficult. But this solution can actually be improved. And more precisely, we can improve our time complexity. And the way that we can improve our time complexity is by taking a look at this isPalindrome function. Because we can kind of think, for our cuts array here, by the way, I forgot to mention that this array we named cuts, even though we didn't really need it for this conceptual overview, but it's good to remember. So for this cuts array, right, we kind of have to do the double for loops that we came up with. There's no other way around it, right? We have to, at every point, we have to iterate first through the string once, and then we have to realize, well, wait, whenever we're at a new letter, we can't just assume that the cut comes before it. Maybe we can form a palindrome, and to realize that, we just have to reiterate through the string. So there's no way of going around the O of n squared time operation of cuts. And even if there were, it doesn't matter because we've got an O of n cube operation here with this palindrome stuff. Okay? So this is where we want to try to optimize. And now in terms of space complexity, let's first look at that. Could we do better in space complexity? Well, no, because we need all those values, right? All the values that we stored in this 2D array, we end up using when we're building our cuts array. Whenever we're checking if a substring is a palindrome, we need this array. So, yeah, we need the space complexity. But so, could we do better in time, right? Do we need to build this in n cube time? And the answer is no, we can do better. How can we do better? We know that we're going to have to iterate through n squared substrings, right? Because that's the number of substrings there are, or it converges to n squared. So we know we need these 2 for loops in our formula. Okay, so we know that our time is going to be at minimum O of n squared for this array, and for a cuts array, it seems like it's going to be O of n squared as well. Okay, so we're saying maybe we could get this to O of n squared. Well, we'd have to eliminate is palindrome, right? Because is palindrome is the culprit that brings us to this cube. How can we eliminate is palindrome? Or can we even eliminate is palindrome? And the answer is yes. We can eliminate is palindrome with a very clever way of building this array and using solutions that we store in this array to build up other solutions. And basically, recall how at the beginning I said that when we built up this first array and we were calling is palindrome, we hadn't really used any dynamic programming tactics. Well, here, we are going to use dynamic programming tactics to build this array in O of n squared time without ever calling is palindrome. And to do so, we're going to realize that, first of all, the first diagonal here is always going to be true, because we know that any single letter, this diagonal represents single letters, right? Letters that start and end at the same index. These are always going to be true because they're always palindromes. And then what we can further notice is that if we're checking if a string is a palindrome, all that we need to check is that the first and last letter of that string are equal to each other, and that the string in between those first and last letters is a palindrome as well. And what if we've already stored that solution in our array? What if we've already stored the fact that the string in between 2 letters is a palindrome or not? If we have, then our computation here for is palindrome just becomes an O of 1 time operation, right? A constant time operation. Because all we're doing is we're comparing 2 letters, the first and last letter, and then we're saying, is the string in the middle, in between the first and last letter, a palindrome? Well, let's just look at our array and see if it is. So that's kind of the gist of it. Now, you might be confused because I haven't really implemented it, and we do have to change. We can't just use these double for loops here. We have to do some really clever shenanigans. But I think it'll be a lot better to explain it during the code overview or during the code walkthrough rather than here on the whiteboard. It'll be simpler and it'll make more sense. So at this point in time, we're going to dive into the code walkthrough, and I'll see you then. All right, so we've got our palindrome partitioning mincuts function defined, and let's start by diving into that naive solution, so to speak. So the first thing we did was we built our 2-dimensional palindromes array, right? Now, we can initialize it to false values, false for I in string, and then we can say for j in string. Remember, this is a 2-dimensional array that has as many rows and columns as our input string has characters. So we initialize it like that, and then we apply the formula that we wrote at the very beginning of the conceptual overview, right? So we say for I in range length of the string. Then we say for j, so I is going to be between 0 and the final index in our string, and j is going to be in the range from I to the length of the string. And recall, we want I and j to overlap at times, right? Which is why here we're saying I and not I plus 1. And we are going all the way to the length of the string in both for loops. But so we iterate through both of these, and then we just say palindromes of I, j is going to be what? Well, we're going to check if the string that starts at I and ends at j is a palindrome. So we're going to call our is palindrome function, which we're going to write in a second. and it's going to take in a string. The string is going to be the substring, right? Where we slice strings starting at I all the way to j plus 1. So that's our first for loop, or first double for loop, and that's how we build up our palindromes array. Now, before we move on to the cuts array, let's quickly write our isPalindrome function. This is pretty straightforward, right? IsPalindrome always takes in a string. We can have a left IDX, which starts at 0, right IDX, which starts at, the final character, length of string minus 1. And then we can say while left IDX is less than right IDX. Here we're kind of doing the 2-pointer strategy, right? We're putting a pointer at the beginning, pointing a pointer at the end, and we're saying if the string at left IDX is not equal to the string at right IDX at any given time, then we just return false. Otherwise, we increment the left IDX and decrement the right IDX, and at the end we return true. If this is confusing to you, this function, go check out the problem in the strings category of AlgoExpert of the website. That's called palindrome check, I believe. And we literally deal with this problem, checking the palindromicity of a string, and we go through various solutions, but this one using 2 pointers ends up being the most optimal one. So that's our isPalindrome function, which we call here in our double for loops. Great. So now we can build up our cuts array. So remember at the beginning earlier, I initialized our cuts array to have infinity at every point. We don't really need this. I just think that, like, for a lot of dynamic programming problems where you're taking the minimum 2 values at one point or another, it's nice to initialize your array with infinity, because when you compare 2 values, like let's say you're literally using the min function in Python or in JavaScript, math.min or whatever, and you're comparing 2 values, it's nice to have float infinity or infinity, because that's always going to be the greater of the 2 values. And depending on how you implement this function, you might actually need to initialize your array to hold infinity. Here you won't really need it, but I'm just going to do it for the sake of good order. So float in for I in string, and then we're going to say for I in range length of string. Remember, we're iterating through our cuts array once, and we say, first we check, is the current string that we're at a palindrome, right? So if palindromes of 0, I, if we have a truthy value there, because remember, we're looking at the substrings that start at index 0 and end at index I. So if palindrome 0 to I is a truthy value, is a palindrome, then cuts of I is just equal to 0. We don't need any cuts if our string is a palindrome. Otherwise, recall that we tentatively set cuts of I to be equal to cuts of I minus 1. Whatever the minimum number of cuts was for the previous substring plus 1, right? Putting a cut right between that previous substring and the current letter. And then we do our second iteration, right? We say for j in range from 1 all the way to I exclusive here, since we've kind of taken care of that case here. We can say if palindromes of j I and cuts of j minus 1 plus 1 less than cuts of I, then we update. So I'll explain exactly what this means in a second, but then we update cuts of I to cuts of j minus 1 plus 1. So what do we do here? We're iterating through all the other substrings that start at index j and end at index I, where j is between 1 and I exclusive. And we say, if that string is a palindrome, then let's check how many cuts we had, what the minimum number of cuts was for the string right before, the substring that came right before, that new starting index, j. Add 1 cut to that, because we're separating that previous substring to the given palindrome that we're at. And if this this value is less than whatever we had currently stored at cuts of I, then cuts of I is going to be equal to cuts of j minus 1 plus 1. Then we update the thing. Okay? And that's it. That's our algorithm, right? Here we can return cuts of minus 1. And here I guess it would be good to point out this thing about the infinity that I put here. If we were to, let's say we were to comment this line out, and we didn't have this here, and here we maybe went all the way to I plus 1 to take care of, like, this case, then here we could do something like, you know, cuts of I equals min of cuts of I and cuts of j minus 1 plus 1, right? And we could take out this whole, like, and part of the if statement. But this, again, this is really, like, up to you. That's why you would have the infinity there. But this is up to you. This is up to however you want to implement your function when you're in an interview. Just make sure you explain your thought process, right? Make sure, like, let's say you were to implement this solution just as I did. Your interviewer might ask you, why do you have float infinity there? Could this be useful in any way? And you could explain, your reasoning. Or, if you had the other solution that I just showed, then you would explain that's why you need the float infinity. But so, as we mentioned in the conceptual overview, this version of the algorithm is going to run in O of n cubed time, and it's going to run in O of n squared space. Let's just reiterate why it's O of n cubed time, because we're calling this is palindrome function here a total of roughly n squared times, and is palindrome takes O of n time to run, right? So this is the first version of the algorithm. Now, let's try to tackle the more optimal version that I vaguely explained in the conceptual overview. Believe it or not, this second version is going to be very similar, right? Because if you remember, this entire portion with the cuts array didn't change, right? The only thing that we optimized was our palindromes array that we built. So in fact, what we can do is we can actually copy paste this, and then let me comment out all of that. So we can copy paste our palindrome partitioning min cuts function, and this entire portion here is not going to be touched. So for now, I'll comment it out, but rest assured, this is going to be in the algorithm, but it's not going to be altered. This is what's going to be altered, okay? And so what we can do is we can delete this, because that's the logic that we're going to do differently, and we can start from here. We've initialized our palindromes array, and now we dive into our new logic. So how does this work? Well, the first thing we do is we iterate once through the string for I in range len of string, right? And we set the palindromes at I. So this is the diagonal, right? The diagonal that I was talking to you about, where the index of the row and the column is equal to each other. We set that to true because every letter, right? Every one character or one letter string or substring of our string is a palindrome. So that's kind of one of our base cases. Or that is our base case. That the diagonal has to be set to true. Okay? And then what we do is we say, well, we're now going to want to look at substrings. We've done all the substrings of length 1, right? These are like palindromes of II represent substrings of length 1. So now we want to look at substrings of length 2 and more. So we're going to say for length, we're going to declare a variable called length, right? For length in range from 2 all the way to the length of the string, because, right, we can have a substring that's the entire string, the length of the string, and then we put the +1 because, this is exclusive, or, range goes to the last value excluded. So we want to look at substrings of length 2 all the way to the length of the string. Then we're going to say for I in range 0, and this is where it gets really tricky, okay? This is why the solution is pretty brutal to come up with just all on your own in an interview, but it's definitely worth exploring. So for I in range 0, len of string minus length plus 1, and I'll explain in a second what this line means. So for all of that, j is going to be equal to I plus length minus 1. Okay? And then we're going to do some logic here. Now we're going to do some stuff. I'll just write pass for now. Okay? So what did we do here? We're looping through this variable called length. I already explained that. We're looking at substrings of length 2 all the way to the length of the string. Then we're saying for all these lengths, we want to have a bunch of starting indices, right? We want to have a bunch of starting indices called I. So if the length is 2, then our starting index, let's say our string had length 9, like in our example, noon ABBA, or ABBAB, or ABBAD, sorry, noon abadi, length 9. So if we're currently looking at some substrings of length 2, then our starting index can go all the way to index 7, right? Because index 7, if it starts at index 7, we can have a substring of length 2. So for I in range, let's take this example. If the length is 2 and the length of our string is 9, then we're going to say this thing here is going to be for I, it's going to be for I in range 0, 9 minus 2 plus 1. So 9 minus 2 plus 1 is 7 plus 1 is 8. This 8 is exclusive, right? So we're actually going for I between 0 and 7. Okay? Let me reiterate this one last time so it really, makes sense to you, because this is, really complicated with all these plus ones and everything. We're saying when we're looking at strings or substrings of length 2, then we want all the starting indices I to go from 0 all the way to 7, because if they go beyond 7, we no longer have substrings of length 2, right? If our string is of length 9. And similarly, when our length here that we're looping goes to length of string, we don't want to have an index I that's going to be 3, because we cannot look at a string or a substring of length, the length of the input string, if our starting index is 3. So that is why we have this funky looking range here for our I index. Okay? So then we say j is going to be equal to, j is the ending index of our current substring, is going to be equal to I plus length minus 1. Why this minus 1? Well, think about it. If the length is 2, and we're at index 0, I is index 0, right? Then to get a substring of length 2, we're going to want the substring that's going to start at index 0 and end at index 1, right? Inclusive. Here we're including both of them. Okay, so if length is 2, then we want j to be equal to I, which is 0, plus 2 minus 1 to get to the index, right? To the ending index. So we're here again, it's really complicated because you've got this whole, this thing where indices, 2 indices that are next to each other, they have a difference of 1, right? 0 and 1 have a difference of 1, yet they represent a string of length 2, and that's really the complicated part. So you really just need to wrap your head around when you're studying through this algorithm and really trying to understand how it works. I urge you to reread these 3 lines here and really try to go through the examples and wrap your mind around why this works and why this is the case, and you'll nail it. So now we can delete this pass, and we can move on with our algorithm. So now we can say if the length is equal to 2, if the current substring that we're looking at is a substring of length 2, then to check if it's a palindrome, all we need to do is say, are the 2 letters of this string equal to each other, right? If we have the string AB, to test if it's a palindrome, all we need to check is A equal to B? If we have the string AA, all we need to do is check if A is equal to A. So palindrome IJ is going to be equal to string of I equal string of J. Simple as that, right? We're testing the equality of the 2 letters, and the letter at the starting index and the letter at the ending index, and saying store that equality, whether it's true or false, in our palindromes array. Okay, and then we're going to say otherwise, if our length is not 2, so if we're dealing with a bigger substring, then how do we tell if the string is a palindrome? How do we fill up this palindrome's I of j? Well, it's pretty simple as well. We check, are the 2 letters equal to each other? Is the first letter and the last letter equal to each other? The letter at the first index, of the starting index I, and the letter at the ending index j. And is the string contained in between the starting letter and the ending letter a palindrome itself? But remember, we're building this array as we go. So we have this value. We have palindromes of I plus 1, palindromes of I plus 1, j minus 1. We have this. We have this stored already. So, like, accessing this is just a simple constant time operation. And that's it. Now we're done. Like, now we can uncomment everything here, and we're done. We finished building our palindromes array. And so this is going to run in O of n squared time, not O of cubed time. And it's going to run the same space complexity, because here, again, we're doing 2 for loops. And if you look at the values in those for loops, they're pretty much equivalent to the values we had in the 2 for loops above here. So we're still like doing O of n squared computations, right, for the for loop, because we're building this O of n squared array, 2-dimensional array. But instead of calling as palindrome, we're doing this stuff here with these 4 or 5 lines, where all we're doing is checking, are 2 letters equal to each other, and maybe is a value that we've already computed beforehand, like previously in the previous iteration or the previous few iterations, is it truthy or falsy? And that's just a constant time operation. This is a constant time operation. All of these 5 lines are a constant time operation. And so we've optimized our algorithm. So this is the most optimal way to solve this problem. Like I said at the beginning, it's complicated. This is not an easy problem. Even the first solution, this solution here, is not easy. I think that like I said at the beginning, it's hard to wrap your head around this stuff with the number of cuts. 2 cuts turns into 3 substrings. It's just hard to wrap your head around, right? And for this solution, I think that the palindrome array building is pretty straightforward, right? Because you're just generating all the substrings and calling this is palindromes function. But then building the cuts array is pretty difficult. Like, that's really difficult, and in my opinion, it's a lot more difficult than other questions like the maximum sum of an increasing subsequence. But then when you get into this more optimal solution, if your interviewer asks you, can you do better, this part of building the palindromes array starts to completely eclipse the cuts array in terms of difficulty. Like, this is really difficult. It's really difficult to come up with this stuff here. But the nice thing here is that if you understand what I just explained in this video, And if you really, really grasp it, then this is going to become a lot more easy the next time you see it, or the next time you see a similar problem. And you might start to or maybe you find yourself in another problem that deals with palindromes, and you might think, oh wait, I can build an array of palindromic substrings in O of n squared time by doing this, right? So try to understand it. I hope this was helpful. I hope this was informative. This is a pretty lengthy video. Hopefully they won't all be as lengthy as this, but I'll see you in the next one.